it was mentioned, my name is Mikołaj Płachta, and I'm from Warsaw University of Technology. And today I want to talk about the simple neural networks for detection various image steganography methods. So, in our world, the modern cyber war threats are evolving. This security of information is more problematic for us. And for that, the kind of problems with steganography could be a thing that we should take care of that. In case my work on detecting image steganography was developed under the CMARC project that was funded by EU Horizon 2020 grant and also Warsaw University of Technology IDUC Mobility Program. So, but starting from the beginning, what is a steganography? Steganography is a practice of hiding the fact of communication and the specific information sent through the medium on the open manner. So, in a short words, for example, we can have a text in which we can embed some kind of hidden information sent through the typical internet, typical email, and nobody from the outside will know that there is something hidden. So it can be used to leak confidential data from websites or secret communication via email. My work is about the checking ability to detect image steganography that it's embedded in the JPEG files. So for the JPEG files, we have three most popular algorithms. The first is JPEG universal wavelet relative distortion, in short J-Uniward. It's a method for modeling distortion during embedding the hidden information. When we embed this information, the image will change in some way, and the coder, the main idea of the coder is that to hide that in that way that we won't see that, or maybe it will be hard to detect, or if there will be problem with hiding that without any changing any statistical things, the coder should also hide that on the places that will be harder to detect. The second is NSF5. The main idea of that algorithm is to modify at least bits of AC coefficients in the whole DCT transform of the JPEG file. The whole idea is rely on the coding a syndrome, and the syndrome is kind of encrypting and decrypting key. And the last one, UERD, Uniform Embedding Revisited algorithm. The idea of that one is to change the maybe image in that way during, of course, embedding the data to make something like that we the statistical things of the image won't change during embedding this data, and that algorithm achieves that during by analyzing the DTC coefficients, whole blocks of DTC, and the neighbors of this specific DTC modes. So on this slide, as we see, there is the same image in the three versions using the three algorithms, the embedded data is the same. So as we see by using our eyes, we cannot detect which information is hidden and if the information is hidden. So this is the main cause of my work and research, to find a tool that will help us detect some kind of threats. To help with that, we used 4 types of features. The first was the easiest one, analyzing DCT, discrete cosine transform, that is mainly used on the lossless compression like JPEG. In that case, for example, when we analyze the JPEG file and making on that the DCT, we are getting a vector of data. For the black-white image, we are getting 1 vector. For the colorful, we are getting 3 vectors, one for luminant channel and 2 for the chrominance channels. On the first stage of our research, we are only using that type of input data, but the results of that wasn't really promising. So we are focusing on more sophisticated ways that it will be mainly described in next slides. So first of that is a kind of modification of or extension of DCT. It's a discrete cosine transform residuals, and simply we are taking for taking this algorithm, we are taking 8x8 pixel filter. And after that, we are making convolution function, going step by step through successive section of the image, and after that we are getting a vector of the data containing a kind of histogram specifically for the specific image. And of course, it behaves similarly to DCT. When we have a black-white image, we are getting only 1 vector. For colorful, 3 vectors. The second one is the GFR. Also, we are getting a histogram at the end, but the main difference to the DCTR is that we are creating histogram from quantized coefficient obtained from 2-dimensional Gabor filters. The third one, PHARM, phase-aware projection model, is a function that uses linear and non-linear filters. And after that, we are applying convolution function with the image. And after that, we are getting few histograms. That this is the main difference from the two previous ones, because in that case we are getting more data for each DCT vector data of the image. And that kind of feature extraction is mainly designed to detect the J-Uniward. That is the most sophisticated and hardest to detect steganography algorithm. Of course, by according to the authors of the research. In my research, I use mainly Keras and plus TensorFlow library because Python has a lot of libraries to help such kind of work and research. On my research, I mainly focus on using simple neural networks, focus on low computation complexity. So it was mainly used dense layers from the Keras library, but also it was we tested things like RNN or convolution neural networks, but we don't get really satisfactional results at the beginning. Like we are focused only on the dense version. Regarding the activation function, we test the most obvious one like sigmoid, softmax, etc. But the best results we got for the ReLU. And we also choose the two most promising optimizers, ADAM and SGD, to summarize kind of testing. On this slide, on the right side, we see the behavior of the ReLU activation function. Regarding the dataset, for the main batch of testing was used a kind of that dataset called BOSBase, really well known in the image steganography world. It contains 10,000 black-white images. We divided that into the 9K as a train set and 1K as a test set. For each of the splitted kind of sets, we prepared a version for 3 algorithms previously mentioned at J-Uniward, NSF5, and UERD. Also for this free version of the steganographic algorithms, we use 2 density of packing the data. So and I mean the packing of the information of the hidden data by every non-zero DCT value of specific image. We choose the values, 2 values for the each kind of data set, 0.4 and 0.1. On the first stage of the research, also it was used a second data set, pretty new one in the steganography world, called Stego 100K. But we have a big problem with that. Because, for example, we noticed that we don't have, we cannot have whole data. It looks like there is gaps on the images. Like we don't have, we only have a kind of hover file, so without any embedded data. But for the steganographic version, we don't have a steganographic version for this image. And the opposite ways, for the kind of part of the images, we have only steganographic version, but without the cover one. Also, we doubt about the proper classification of these images and labels. So we contacted with the authors, but we don't get any response. So we are focused on the first one, BOSBase. So on this slide, I'm presenting the kind of solution of my solution scheme of my proposition. So at start we have image of the pixels. After that, we are making a feature extraction by DCTR, GFR, or PHARM, and making a histogram that will be an input for the neural network. And my kind of neural network will be containing a kind of parts, and a part containing a dense layer and normalization layer. For our research, we tested few configuration. We tested containing neural networks that have 2, 3, 4, and 5 parts. But we observed also that going through the more than 3 parts, there is no any income, and there we are getting worst results on that. So we are give up on that, and I will present the results only for 3 and 2 layers configuration. So in this slide, I'm presenting the accuracy on the test sets. This is the most important thing. As we see, I chose 5 of the configuration, those most relevant ones. As we see, the network architecture is on major of the ones we have 3 layers. One is for the 2 layers one optimizer. We choose different optimizer, different learning rates, and for each configuration we test a version with the each feature extraction parameter. And after such analysis, we see that the best results we get for the DCTR, but also GFR has kind of looks really promising in that way. The PHARM got the worst one. And for the best configuration, we making rock curves and calculated metrics like precision or recall that give us ability to check if we have a lot of false positives, etc. So as we see, the difference between accuracy and precision recall metrics is not super high. It's pretty the same. So looks like model is not overtrained. But there was a problem with this solution, because on that way we have 6 models detecting each of the configuration. If, for example, for NSF5 0.4, we are detecting only the NSF5 0.4. But the main idea of the SIMARC project was to develop a kind of unified tool. So in the later stage of the research, I've made kind of cross-testing, and the results is shown here. This is also results of the accuracy. So we have 6 models that try to detect every kind of previously prepared steganography dataset. So as we see, the best result we got for the configuration with the model of J-Uniward 0.4. And for that configuration also, we prepared rock curves and the precision recall metrics. So as we see, the results is slightly lower, but in that situation, we are sure that we are pretty able to detect most of the such kinds of algorithms in only using the one model. So it looks really promising, and that gives ability to continue this research. So my conclusion after this batch of research is that first, that batch normalization layer increase the obtained results, and it is really needed. For example, for NSF5, I've got around 15 to 20% better results. And for example, for J-Uniward 0.4, I've got an ability to learn this model, because without this layer, I don't have an ability to do that. Also, we see that simple neural networks can learn quickly and allow detection with pretty high accuracy. But we still have a problem with 0.1 version for J-Uniward, because this is the tough one algorithm. But also in the literature survey, we also see that the other people have a problem with that. The values obtained, as I mentioned previously, for PHARM coefficient are relatively worse in relation to DCTR and GFR. Also in literature survey, I observed that UERD set is between J-Uniward and SF5 results. And also in my kind of research, also I've got pretty the same kind of relativity. So I think that my work was done properly. In the literature, mainly was used a kind of set that, for example, I mainly use batch normalization dense model, but on literature, people use convolution batch normalization dense. And my results, it's not super worse than the more complex one containing the convolution part. So this also looks promising. And the last one about the J-Uniward 0.4, that model works really properly in the most of the combination of the algorithms. But on the next stage of this research, I will test kind of hybrid combination with multiple best models. And I think that will be all for today. Thank you for listening, and I'm open to questions.